In our study of applications of integration, we now want to turn our attention to some physics-related topics. For example, we're going to talk about work, about mass, about force, and about pressure. We'll be looking at work systems in springs, and we'll also look at the work required in order to lift liquid out of some type of container or vat. We're also going to take a look at the force exerted by a liquid, in our case, water, on a vertical surface or a flat surface, horizontal surface, submerged in the water. In other words, hydrostatic force and hydrostatic pressure. I'm going to divide this section into 3 different videos so that each video can be somewhat shorter. You'll find that the integration is relatively simple. It's the development of the formulas that takes a little bit more work. Let's go ahead and get started, and let me share my screen with you. So what we want to start with is we want to start talking about some of the definitions that we're going to use to talk about work and force. So the first thing that we want to study is the amount of work done by a force when it moves an object through a distance. That's really what the physics sense of the term work is needed. So let's talk about some more things that are involved in finding work. One of the first things is you need to know what a vector is. Now, a vector is a quantity that has both magnitude and direction. So velocity is a vector, but speed is a scalar. A scalar is a quantity that only has magnitude. It does not have direction associated with it. So another example of a scalar would be distance. Your distance is, well, I'm 5 miles from the store. That's your distance, which is a scalar. Now, velocity is considered a vector because it has both direction and magnitude. Speed would be 60 miles per hour. That's a scalar. But 60 miles per hour north, that's velocity. You're giving both the magnitude, 60 miles per hour, and the direction of motion, which is north. The next thing that we want to talk about is mass. In order to do many of the problems, we have to be able to compute the mass of something. When we talk about mass in physics, we are not talking about your weight. The weight is something different. Weight is actually the gravitational force on the mass of your body or an object. So mass is actually a measure of the number of atoms and molecules that make up the object. So mass is a measure of stuff, if you will. It's generally measured with kilograms and grams. Now, we don't really measure mass in the English system, though technically we do have one. It's called the slug. And this is the mass that is accelerated 1 foot per second, 1 foot per second squared, when a force of 1 pound is exerted on it. And it's called a slug. No, I didn't make that up. Now, the next thing that we want to talk about is density. Density, in this case, is a measure of the mass of an object per unit of measure. Now, if we're considering it to be a one-dimensional thing, like a really thin wire that we can sort of pretend it's really only one-dimensional, as in it has length but no width or height, then we can say that the density is density per unit of length. Or we can talk about something that's really, really flat, like a sheet of paper. It's not really 2D. It is still 3D. It does have thickness to it, but we can pretend that it's 2D, and then we can talk about the density per unit of area. Most things, of course, in the real world are really 3-dimensional. And when we talk about 3-dimensional objects, we tend to talk about the density as the mass per unit of volume, often kilograms per meter cubed. Now, what we want to turn our attention to are some other objects that we want to measure. One thing I do want to mention before we move on is that the density of water will come up quite often in quite a few of these problems, and it is 1,000 kilograms per cubic meter, which is quite a lot. Now, we don't really use mass in the English system other than the slug. And so it doesn't have what we call a true density, but we do have what's called a weight density of water. And that's 62 pounds per cubic foot. Now, I said that pounds weight is actually a measure of the gravitational force. So it's actually a combination of the gravitational force and the density. So what you have for the weight density is a combination of the force, gravity, on the volume. So we've got pounds per cubic foot, 62.4 pounds per cubic foot. So we can find the mass then if we have a one-dimensional object by taking the density and multiplying by the distance, the only dimension it has. If it's two-dimensional, we take the density, we multiply by the area. We'll see this one get used when we talk about hydrostatic pressure and hydrostatic force, because we often want to know what the pressure is on the surface of something, like the surface of a dam. So it's vertical in the water, and we can consider it to be roughly 2D, all right? And then if we want to compute mass for lifting water out of tanks, then we have volume. So to get the mass, we take the density of water, which is 1,000 kilograms per cubic meter, and we multiply by the volume of water that we have. And that will give us the mass of the water. Now, when the density varies, such as if you have different parts of the object made of different materials, then you need calculus to do that. So for example, if you had a flat plate and one side of it was made of aluminum, which is not very dense, and then the other side was made of something like iron, which is very dense, then the density is going to vary as the composition of aluminum and iron changes across the surface of the plate. And to do that, we need calculus. So we want to talk about the mass density formula for the one-dimensional case first. Now, in the one-dimensional case, what we're really looking at is a very, very thin wire. So we're thinking of it as being so incredibly thin that it only has length. It doesn't have width or height. Now, of course, that's not the real world, but it's an approximation that works pretty well. So in this case, what we're going to do is we're going to find that the density may depend upon the position in the object. If that's the case, in other words, one end of the wire is made of aluminum and the other end of the wire is made of, I don't know, tungsten or something like that, so that the composition of aluminum and tungsten is varying across the wire, then the density is also varying across the wire. Then what we can do to compute the mass is take the density function, which depends on the position, where you are on the wire, which of course is going to tell us the composition of aluminum to tungsten. And then you can multiply it by the differential dx and integrate from A to B, where you want to know what the mass of the wire is, say from 1 foot of the wire over to 3 feet on the wire, then you'll know what the mass of that section of the wire is. Now, how are we doing that? Well, we're doing what we always do in calculus. We're doing the calculus thing. And the calculus thing, of course, is to take the wire, and again, we're assuming it's infinitely thin. Here it looks 3D, but we're assuming it's infinitely thin, like a line. And we're chopping it into tiny little pieces. In other words, we're taking a partition. So we're going to partition the wire from A to B, x equal A to B. This is the section of the wire. I want to know its mass. And over each little section, if I make them narrow enough, small enough, then I can assume that the density on that tiny, tiny little sliver is constant. Now, of course, it's not really, but if I make it narrow enough, it's a pretty good approximation. And of course, we're going to do what we always do in calculus. We're going to allow the widths of these partitions to go to 0 as we increase the number of partitions to infinity. Sounds like a Riemann sum, and of course it is. So what we're going to do then is we're going to compute the mass of each individual little slice by taking the density function rho of x and multiplying by delta x, which is the length of that particular slice. So we know that rho of x depends on the position and delta x is the width. So the mass of this little section will be rho times dx. Now, when we look at it, of course, it is a Riemann sum. And that's what allows us to take the limit as n goes to infinity and to get the definite integral that you see up here. So now we want to take a look at our first example. We have example 1. We're looking at a thin rod. It's oriented on the x-axis just to make it easier. And we're interested in the section of the wire between 1 and 3. So I don't know how long the wire is, but I want to know how much the section between 1 and 3, how much mass it has. Can't say how much it weighs, but I can say how much mass it has. Now, the density of the rod varies along the length of the rod. According to the formula, rho of x is equal to 2x squared plus 3. This is rho. It is the Greek letter r, even though it looks like a p without the stick on it. So it is r. So we're going to take this function right here, and we're going to use our formula that we just got a minute ago to compute this. So remember that our formula is going to be from a to b, rho of x dx. And this will give us the mass of that section of the rod. So in our case, we want to integrate from 1 to 3. Rho of x is 2x squared plus 3 dx. Now go ahead and pause the video, compute the integral, and then turn the video back on and we'll compare our answers. Shouldn't take you more than 30 seconds. So hopefully that didn't take you too long. It's a pretty straightforward integral, and it gives us 70/3. So that must be a measure of the mass. It didn't say what it was, but we can assume maybe it's grams or kilograms, something like that. Now we want to go ahead and think about something else. We're not going to be able to handle the 2D case and the 3D case until we get to calculus 3. In calculus 3, we'll learn how to work in 2 and 3 dimensions better, and we'll be able to have variable density across area and variable density across volume. And we'll be able to figure out what the mass is, even in those cases. However, we can look at one special case in the 2D case, and that's called mass density for a flat disk with radial density. Now, what does that mean? Now, when we're talking about a disk, we're really talking about, well, a circle. So we have a disk and it's flat. And by flat, we mean infinitely thin. So it's like a sheet of paper, but shaped like a circle. And it has radial density. Now, what that means is that if you take the center of the circle and you measure to the edge, the density is varying with the radius. So the density depends upon the radius of that disk. So this is the one special case that we can still do in calculus 2. So we're assuming then that rho, our density, is given in terms of mass per unit area, because it is a flat two-dimensional object called a lamina. That means flat two-dimensional space. Ours is a disk, it's a circle. Not all laminas are circles. And the density only varies according to the radius, and this is radial density. So what we're going to do is we're going to let rho of x represent the density function. We're going to put the center at the origin, and then we're going to partition along the x-axis. Now, as we do this, we end up with a set of concentric circles. These are called annuli. They're actually ring shapes, right? They have a little bit of width to them. So what we have here is we have the center right here, and we divided the x-axis here into partitions. And each partition, because the density varies radially, it creates these rings. You can see the blue ring, the green ring, pink, yellow, and purple as it comes out towards the outside. On each individual ring, if we make the ring super, super thin, which these are not thin enough. I mean, if I made them thin enough, you wouldn't be able to see them. They'd look like lines. So if we make it thin enough, then we can approximate and say that the density on each individual annulus is constant. And then because we do that, we can compute what we think is the mass of each individual ring. Add the mass for all the rings together, called annuli. And then, of course, we're going to take the limit. As n goes to infinity, the number of annuli increases. So again, what we've got here on each of these, in order to find our density, or a mass using density, we're going to have to know what the area of each annulus is. Now, the area of the annulus, this is one annulus pulled out over here, and you can see it's not the full circle, it's the ring shape. And what you have is an inner radius, lowercase r, and an outer radius, uppercase r. So of course you do what you think you do. You take the outer one, pi uppercase r squared, and you subtract the inner one, pi lowercase r squared. Now, if you do that, you end up with the formula that you see here. So you end up with pi times x sub k quantity squared minus pi times x sub k minus 1 quantity squared. Why x sub k and x sub k minus 1? Well, that's the width of each individual annulus, because each partition marks where the next annulus begins. So we take each of these and we square it. We can factor the pi out. Now we do something kind of tricky. Because this is the difference of two squares, we factor it. So we get x sub k minus x sub k minus 1. That's where each partition begins and ends. And then times x sub k plus x sub k minus 1. Now, x sub k minus x sub k minus 1, well, that's just delta x. That's the width of our little annulus. So this part becomes delta x, and we get x sub k plus x sub k minus 1. So if we're thinking about that, as the annulus gets narrower and narrower and narrower, these x sub k's and x sub k minus 1s get closer and closer together. So we can approximate it with some random point somewhere in between. So we might call it this point right here, x sub k star. So that's some random point in between x sub k minus 1 and x sub k. And we're going to take that and double it instead of adding x sub k and x sub k minus 1 together. It's an approximation, but as those widths get narrower and narrower, it's a pretty good approximation because it is narrowing down almost to a point. So it is almost like doubling the point. So then we get 2x sub k star to replace the x sub k plus x sub k minus 1. And our formula then becomes the following. For our formula, we get a sub k is approximately equal to 2 pi x sub k star times delta x. Now, the 2 and the x sub k star came from the x sub k plus x sub k minus 1. And we just inserted the pi in the middle because it was a good place to put it. And then the x sub k minus x sub k minus 1 becomes delta x. So this is the area, which basically was the area of the outer ring minus the area of the inner ring. So these are equivalent. Now this is going to give us the area of the kth annulus, and then we're going to want to add them all up in order to compute. Now, before we add them up, we need to find the mass of the annulus because that's what we're looking for. So to get the mass, we take the area and we multiply by the density. Remember, the density is going to be density per unit volume or per unit area or per unit length, depending on whether it's 3D, 2D, or 1D. So we have 2 pi x sub k star times rho of x sub k star delta x. And now we're going to sum over all of the annuli. And we end up with this integral that you see here. From 0 to r, however far out on the disk we want to go. And we may want to go from 1 to 3, like how much does that section of the disk, how much mass does it have? Or we might want to go from 0 all the way to the edge of the disk, and that would be the total mass of the disk. It's going to be 2 pi x rho of x dx. So it's a pretty straightforward formula that we have here. So we're going to start with our formula, which is the integral from 0 to however far out we're going to go, 2 pi x times rho of x dx. Now, you may be wondering, well, where does x come into this? Remember that we superimposed the xy coordinate system onto our disk, and that the center of this disk is right there at the origin. And that means that the radius is actually the x coordinate. It's also the y coordinate, but we're going to think of it as the x. So the radius can be measured with the variable x. So r is actually x in this case. So now what we want to do is simply apply the formula. So again, I invite you to pause the video, go work it out, and then turn the video back on and we'll compare answers. So let's see how you did. When you multiply it out, you get 6x squared plus 4x, use the power rule for integration, and you finally compute that you have a mass of 24 pi units, whatever your units happen to be for mass, whether it's kilograms or grams. Now what we want to turn our attention to are some more definitions. So we want to start talking about work and force. And to do that, we need a few more definitions. Weight, we've already discussed, is actually a measure of force. It's the force of gravity on a particular object. So the more mass an object has, the more atoms and molecules, the greater the force exerted by the gravity and the greater the weight. Now, your mass is the same whether you're on Earth, on the moon, or floating in space. You have the same number of atoms and molecules in all three places, but your weight will change. So your weight when you're on Earth is a measure of our gravitational force, 9.8 meters per second squared, or 32 feet per second squared. And that's exerted on the atoms and molecules in your body. So you weigh a certain amount. When you get to the moon has less mass, so it exerts less gravitational force, and you weigh less on the moon. You have the same amount of atoms and molecules. Your mass is the same, but your weight is less. Now, in the vacuum of space, you have no weight at all. So you would weigh nothing because there's no gravitational field being exerted on you. But again, your mass would be exactly the same. Now we want to talk a little bit about acceleration. Acceleration is a vector, just as position and velocity can be considered vectors. They have magnitude and direction. It's going to be represented as a change in velocity with respect to time. It's often measured in feet per second squared or meters per second squared, something like that. Now, gravity is measured by its accelerative force on an object. That is, we think of gravity itself as an acceleration. It exerts a force on us. That force is weight. But we consider gravity itself to be an acceleration. And this is how it is typically represented. Now, in physics, a lot of time, these would be negative because they consider that it's pulling you down and they call up the positive direction. In this class, we're just going to let them be positive and we're not going to worry about the direction part of the vector component. Now, what we want to talk about is force. What is force? Force on an object can be thought of as a push or a pull on an object. And this is going to be some kind of interaction between the two objects. It can be measured in a lot of different units. There are lots of units of force. In the metric system, we typically use newtons with an uppercase N, named for Sir Isaac Newton. And a newton is equal to a kilogram meter per second squared. So 1 kilogram moved 1 meter per second. That's 1 Newton. All right, so we see that we have this relationship here. Now, what is Newton's second law of motion? So this is Sir Isaac Newton back in 16, whatever it was. He founded calculus along with Gottfried Leibniz. He published in 1692. So that's when calculus first got its start, but he came up with the law of motion quite a long time before that. So what does it state? This is the one that many students whether they're mathematicians or engineers or not, they actually know this one, F equals ma. It's very simple, but it's very powerful. It says that the force acting on an object is equal to the mass of the object. Now that's mass, not weight. Mass, a measure of atoms and molecules, times the acceleration. And our acceleration, of course, is going to be due to gravity. So in our case, this ma is often going to be an mg for mass times gravity. Now, what is work? If we think about work, work is basically some kind of force exerted through some non-zero distance. Now, here's the weird thing. If you push on something like a wall with all your weight, I mean, you really shove on the wall, but the wall doesn't move because walls don't move, then you've done no work, at least in the external physics sense. You've done internal work inside your body. You've had some chemical reactions going on with your muscles using energy. That internal work does not translate to external work. If the wall doesn't move, no matter how much force you applied to it, no work was done. All right. So it's very important to know that it actually has to move for there to be any work done. So we think of this as a force through a distance. And this becomes work is equal to force times the distance through which it moves. Now, it can also be measured in different units. In the metric system, it's a joule. Now, a joule is a Newton meter. So that's the force, Newton, times the distance through which it moved, 1 meter. So a Newton meter is a joule, and it's often written something like this. And because a Newton is a kilogram meter per second squared, a joule is a kilogram meter squared per second squared. Now, you can also express work in things called ergs, which are very, very small, 10 to the negative 7 joules. Electron volts, 1.6 times 10 to the negative 19 joules, tiny, tiny little things. We can talk about the horsepower hour. We can talk about cars. Then you've got something that's pretty whopping large, 2,684,519.54 joules. We have a kilowatt hour, which is even bigger, 3.6 times 10 to the 6 joules. And we've got the liter atmosphere, which I did not give you that one. In the English system, work can be expressed in what are called foot pounds. Now, 1 foot pound is 1.35582 joules, roughly. All right, so a foot pound means that you've moved a pound through a foot, all right, or a pound of force was applied that moved an object through 1 foot. Now, again, if there's no movement, no distance change, no work was done from the physics standpoint. So now we want to put together sort of what we have so far. Work is force times distance. Force is mass times acceleration. So work is mass times acceleration times distance. And if the acceleration is gravity, then it would be mass times gravity times distance. Now, this assumes, of course, that the force is a constant force, that you never vary the amount of force that you're putting on something. And this is typically not the case. Sometimes we start off pushing a little bit and we push a lot harder and then we ease off because we get tired. So the force exerted at any point in time is actually varying, it's changing. And when we think about that, we are again going to have to use calculus, because if the force is not constant, we're going to have to divide that distance into tiny intervals. We're going to take a partition like we always do. And if we make the distance through which it's moved, if we make the partition small enough, then we can approximate the work done on that tiny little partition by assuming the force in that tiny partition was roughly constant. And then we can find the work for each little partition, then we add them all together, take the limit as the number of partitions goes to infinity, limit of a Riemann sum, and of course we get the definite integral. So here it is right here. So again, we're taking this distance through which it was moved, and we're dividing it into tiny little pieces, each little delta x's. And of course, delta x and dx are the same, not delta y and dy, don't go there. Close, but not the same. But delta x and dx are the same. So this is the force applied through this tiny little distance. And then we integrate from A to B, and that gives us the total work done. So now that you have an understanding of the terminology in physics related to work and force and mass, what we want to do is turn our attention to springs. So we're going to talk now about the basics of a spring system. We're not going to spend a lot of time here because you'll get this a great deal in your calculus-based physics class. We're just going to cover the basics. We're not even going to do it the physics way exactly. We're not going to worry again about the directionality of it. We're just going to look at the basics of what happens in a spring system. Now, there are lots of different kinds of springs, and you see a bunch of different ones up here. The one we're going to be focused on is this first kind, which is called a compression spring. It's also a linear rate spring, meaning that the distance between each set of coils is always the same, all right? And the thickness of the coil is uniform. It's the same throughout the entire spring. This one right here, where they're more tight together, this is a tension spring, something you might find on a trampoline. This is another compression spring. This is a spiral spring. I'm not even sure how those work. This is a torsion spring, which you get on clothespins and chip clips, right? They're the things that create that you press on it and it opens up, or you let go and it closes back down. That's that action of opening and closing. That torque is given by a torsion spring. Now over here we have what's called a linear rate spring, a progressive rate spring, and a dual rate spring. You can tell on the linear rate that the distance between the coils is the same all the way across. On the progressive rate spring, you can see that the distance was wider, but it got progressively closer together as you move from one end of the spring to the other. This last one is a dual rate spring. It doesn't progressively get from one to the other. It immediately jumps from one to the other. So this end of the spring has this distance between the coils, and this end of the spring has a smaller distance between the coils. So that's a dual rate spring. We're going to be looking at the linear rate compression spring, and we're going to ignore friction. Something you would technically need to worry about, but we're going to skip it. So when we're talking about a spring, any kind of spring, you know, like a slinky, has a natural length called equilibrium. Now that's when it's at rest, all right? So it's not being pulled and it's not being compressed. It's just sitting there at its natural length, and that's called equilibrium. If you want to compress it, it's going to take some force to push it together. If you want to stretch it, it's going to take force to pull it out. There's no force required to sit it at equilibrium. And I have a couple of pictures here to show you what it looks like. So this is one from the OpenStax textbook, and this shows the spring, this jagged line here, which doesn't really look like a spring, but okay. So this is what it looks like at rest. And we tend to call the rest position, the equilibrium position, the origin. So that's where it starts. Now, in this case, you can see that they moved it to the left by compressing the spring. This blue thing on the left is maybe a wall or a board that's fixed in place and can't move. So if you push, the distance between the coils gets smaller. You can see it gets smaller, and that requires force. Now the distance went to the left, so it's a negative distance. If you want to elongate or stretch out the spring, you can see that the distance between the coils gets larger. And in this case, it moved to the right, so X is positive. In both cases, it requires force to either stretch or compress the spring. Now, in this picture, the resolution is not as good, but these at least do look more like springs. Relaxed would be right here. This is at equilibrium. This is where it is stretched, and you can tell the X has gone to the right, and compressed, X has gone to the left. Now we want to talk briefly about Hooke's law, at least as we apply Hooke's law in mathematics. Hooke's law basically says that the force required to compress or stretch a particular spring, like this one, from its equilibrium position is given by the force equal to kx for some constant k. Now, what does k depend on? K is called the spring constant. And so when we're looking at the spring constant, what would make it be different? Well, it depends on the diameter of the coil, right? So the diameter of the wire that makes up the coil. The thicker they are, the harder it's going to be to stretch or compress. It also depends on how tightly wound they are. So remember when we were looking up here at the tension spring, these are very tightly wound, whereas on this one, the compression spring, it's much more loose. It's going to be easier to pull this apart than it will be to pull this apart. And then the diameter of the coil itself affects how easily it's going to be compressed or stretched as well. It also depends on the material of which it's made. So if it's made of aluminum, it might stretch more easily than if it's made of iron or something that doesn't really have a lot of flexibility to it. So the material it's made of is going to affect it as well. All of these things get put together and they're called the spring constant K. So the force is going to be proportional to X, right? So we have K times X, and it's going to be proportional to it. Now, X, of course, is the distance through which we moved it, according to the spring constant, that proportional amount. So we want to take a look at example 3 now. We have a force of 8 pounds, which is used to stretch a spring 6 inches from the equilibrium position. We want to find how much work is done to stretch the spring 1 foot from the equilibrium position. So we have to first find the proportionality constant, K, the spring constant that we've got here. So the first thing that we want to do is we want to imagine what is happening in our picture. So we have this spring coming out like this, and it's sitting at equilibrium. And then the next thing that we do is we stretch the spring. So our origin is still here. This is still the origin. And this distance right here is 6 inches. Now, first off, remember that when we're looking in the English system and we're working with pounds, that the measure of force is going to be the foot pound, not the inch pound. So we need to convert the 6 inches into a foot measure. So our 6 inches is going to become 1/2 of a foot, or 0.5 feet. So what we want to know then is, what is the constant? I know that the force is changing, so I want to know how much work is done to stretch it, for which I'll need an integral. But before I can integrate, I need to know what the spring constant is. So my spring constant is given by the original information. 8 pounds has to equal some constant times the 6 inches, which we converted into 1/2 of a foot, right? So this will tell us, because I know it took 8 pounds of force to move it 1/2 foot, then I know all the 3 pieces of Hooke's law except the spring constant. So I can solve for the spring constant, and I get K is equal to 16 pounds per foot, right? So now that I know that K is 16 pounds per foot, now I want to look at the next situation, which is stretching it 1 foot. So I didn't draw that one, but let me see if I can move this down a little bit, and I'll add the picture in. So this is even stretched further. This, of course, is the origin, and this is now 1 foot. So again, it's asking how much work does it take to move it from equilibrium out to 1 foot, and we're stretching it. So I want to write the integral that we had previously, which is the integral from a to b of f of x dx. And that will give me the work. That's force applied through a distance. So the force, of course, is given by K times X, where K is 16 pounds per foot times X. So now I can integrate and I get the work done from equilibrium, that's at 0, the origin, out to 1 foot, so 0 feet to 1 foot, of 16 pounds per foot times X dx. And then you integrate. So go ahead and pause the video. You may not even need to pause it. You could do it in the time it takes me to tell you to pause it, and then compute the integral and turn it back on to compare our results. So let's see how you did. Again, it's a very, very simple integration here. You get x squared over 2. 16 divided by 2 will give us 8 pounds per foot. And then you need to substitute your limits of integration. 1 foot squared is 1 foot squared, and 0 feet squared is 0 feet squared. And that gives me 8 foot-pounds. And again, that is a measure of work done. Now we want to consider the same situation again, but we want to look at something a little bit different. For the same spring that we had in example 3, so we have the same proportionality constant, the same spring constant. So we know already that K is equal to 16 pounds per foot, because that is constant on each individual spring. And this is the same spring, so it has the same constant. How much work is done to stretch the spring 4 feet from the already stretched 1 foot position? So it's already been stretched some to 1 foot. And now we want to stretch it further out here. So another 4 feet. All right. So we're going to be integrating from 1 foot out here to 5 feet. All right. So we're integrating from 1 to 5 because we have from 1 foot, we move 4 feet. That gives us 5 feet. So if you want to, you can pause the video and work it out, or you can just hang loose while I write it down really quickly. 16 pounds per foot times x dx. And we get the same formula we had before, which I'm going to skip the interim part. Gives us 8 pounds per foot times x squared between 1 foot and 5 feet. This is going to give us 8 pounds per foot times 25 square feet minus 1 square foot. And if you work that out, you get 192 foot-pounds of work done. All right, so 192 foot-pounds. Now we've stretched it from 1 out to 5, a distance of 4 feet. My question to you now is, if I move it 4 feet again, but I start at 2 and move to 6, is it the same amount of work done? So now think about, it's already stretched and you're going to have to stretch it more. Is that going to take more force or the same amount of force because the distance is the same? So think about it logically, and we're going to work it out mathematically. So we have exactly the same spring that we had before. And what we're going to look at now is we're going to go from 2 feet to 6 feet. So essentially, we have from 2 feet to 6 feet of 16 pounds per foot times x dx, which we have already integrated this quite a few times. We know this will result in 8 pounds per foot times x squared between 2 feet and 6 feet. And when you plug in those values, you're going to find that the work needed is greater. It takes more energy to stretch further an already stretched spring than it does one that has been less stretched. So when it's already been stretched some, it's harder to stretch it more, if that makes sense. So this turns out to be 256. It's not approximate either, it's exact. 256 foot-pounds of work done. Now, this is the same distance. I moved it 4 feet, from 2 feet to 6 feet. I moved it from 1 foot to 5 foot. It took 192 foot-pounds. But to move it from 2 feet to 6 feet takes 256. It's already stretched more. It takes more than to stretch it even further. Okay, so this is basically the end of this particular video. In the next video, which is also from the same section, 2.5, we're going to be looking at moving water out of a tank. So I hope you'll join me for that video.